All right, good morning, everyone. Welcome to the seminar. So today we are fortunate to have Dr. Thomas Pohlmann. He is in Indonesia right now, but he is a research scientist at the University of Hamburg with the expertise in theoretical oceanography. So today we were informed that Dr. Pohlmann will give us a lectures on climate change in Asian waters and simulations of transport in the ITF regions. I think with his expertise, he has a lot of many studies before, and it'd be interesting to apply that, continue to apply that in the Indonesian waters with many mysteries, and there's so many we can do in terms of the modeling aspects of it. But let me share a bit that Dr. Pohlmann has been also working with Indonesian scientists, collaborating with Indonesian scientists. On 2012 to 2014, he was involved in the BMBF SPY-3 SISCA, which is on the investigations of the carbon transport in the Indonesian waters by means of model simulations and specifically design field campaign. So without further ado, we would like to give the time to you, please.
Okay, thank you very much for inviting me. I will share the screen, if I may.
Yes, you may.
Okay, then I just try to find my presentation here. Yes, it should. Okay, so very good. So thank you very much again. And yes, I'm happy to give a presentation to these to the Deep Sea Center. The talk is about, as you already mentioned, climate change in Asian waters and the transport in the ITF region. It is a main collaboration between me and my very long-time worker, Bernhard Meyer. So I also I'm proud to mention him here because he has done many of the work I will present as well. Okay, I'm from the Institute of Oceanography, as you already mentioned, which belongs now to the Center of Earth Science and Sustainability, how we call it now. So this is a center which is also very much interested in climate research, and this is very typical for our institute because we are the neighboring institute to the Max Planck Institute for Climate Research, which is one of the, I think the leading institute in Germany for doing climate research. And we have also access to our supercomputer. We just got a new one, high performance computer for, especially this computing center is especially dedicated to support climate research studies. Okay, then I may start with my presentation about the ITF region. Probably the Indonesian colleagues know it much better than I. The ITF region is a very important region because it is part of the world conveyor belt, and it has a strong influence on the climate in Southeast Asia and also in the Eastern Indian Ocean. Therefore, because it's in this conveyor belt, I've pointed out here that there is some, this is here, some kind of bottleneck because it transports the warm water back to the downwelling regions in the Arctic and Antarctic regions. And this is the only region where there's a connection between, in the upper waters, between the Pacific and the Indian Ocean. And but on the other hand, it is very complicated and a highly variable current system, and therefore we can call it in principle immeasurable because there are so many different, it has quite a very complex behavior, and this is not only one, this through flow is not just taking place through one passage, but through several, and therefore it is quite very difficult to measure it, and therefore this is a good reason to apply a model system to this area. Okay, so yeah, this is a general sketch again. I think this tells you just that you have a lot of in the equatorial areas there are use these different currents, in particular here on the in the area of the Pacific. You have the different current systems, and this Indonesian through flow is part of this large scale current system. Okay, and this is our actual area which we try to simulate with our model. We call it our ITF region, and we apply our model HAMSOM to this area. HAMSOM is the backbone of our modeling in our group in Hamburg, where this is this Hamburg Shelf and Ocean Model, which is has been designed already in the, I would say, nearly 50 years ago. So it is a very, and it has also, as I realized yesterday, still a lot of applicants here also in Indonesia. Okay. Just try to continue. Okay, this is a very small, brief information about the Hamburg Shelf Ocean Model. You have to use, for sure, you have to, as any model, you have to initialize it, you have to give it additional information on river runoff, initial temperature and salinity distribution, but the symmetry data is very important, and the open boundary values and the atmospheric forcing. This is the input, the additional information that such kind of model needs, because without having this information, you would not be able to get realistic results. And I think the symmetry data is quite, in our case, this, the thing I should mention is that the HAMSOM model is able, due to its specific characteristic, the semi-implicit scheme, which I would not mention here. I can, if someone's interested in this, I could give some information. It's not really necessary to do a lot of smoothing of the bathymetry, which in former times for many other models, they have to smooth the topography drastically, because in particular in these Indonesian slough area, you have very steep topography gradients. And this is not in the HAMSOM model, it's not really necessary. It's not necessary to smooth these steep gradients out, because the model is very stable with respect to such steep gradients. The output of the model then is very standard. We output the sea surface height, the velocity and transports, and the temperature and salinity distribution. As well, we can also give, I have not mentioned here, also with the velocity, also give some mixing parameters, because due to the, we have some mixing scheme in the model, and the mixing is can be also, is an output parameter as well, which depends on this. It's some kind of combination of the velocity shear and the temperature and salinity gradient. So this is something where the mixing is parameterized. Okay, and in addition, we could have sea ice, which is not important here for the Indonesian areas, but we also can include the suspended particulate matter, which is in our case can be done, but we have not applied this at the moment to the Indonesian area. Okay, just the last slide here on the model itself. It is forced from the, as I said, it is a regional model, so you need some information on the open boundaries. It is forced by a global MPI-OM model. This is which is also used for the IPCC reports, and this model has a resolution of 24 minutes. It has 40 layers with a thickness between 60 and 600 meters. It is, and this model is forced by the NSEP forcing. So this is just the for hindcast simulations we use this NSEP forcing. This is at that time where we did this investigation. Normally we also use now ERA 40 or ERA 5 data. I think the ERA 5 data are now the most recent ones. So if you are referring to some hindcast meteorological forcing, then I would recommend to use not the NSEP anymore, but the ERA 5 data. We also have to, these are used as boundary values, as I said. And then we have the regional HAMSOM model, which is then our the model which we are applying, which has a resolution of just 5 minutes with around 10 kilometers, and it has 31 layers. So it is a really fully 3-dimensional model. At this, as I said already, realistic topography, not a big amount of smoothing of the topography, which is also one of the exceptions. If you see other model simulations for this area, people have to apply a lot of smoothing to the topography. NCEP forcing again, so the model is also forced by NCEP, so this which is consistent. You should just make sure that you have consistent forcing parameters, and at the boundary values we use the MPI-OM. I think this is everything I want to tell you. This is the MPI-OM grid, which is then here providing the boundary data to our ITF region. Okay, this is a model domain itself. By the way, if someone is interested or has some problem to understand anything, or please just interrupt me or raise your thumb here, and I would be or raise your hand in Zoom, and I would be happy to answer any questions in between, because if there's something unclear, I would be happy if we could clarify this just at the very beginning. Okay, this is the model, the domain that we use, and as I said, this is you know it better than I do. The Sunda Shelf and the shelf area here, Gulf of Thailand Sunda Shelf, and the Java Sea Shelf. So this is the shelf area, but it has a lot of, which makes it normally complicated for other shelf models. It has very steep gradients here towards the more oceanic areas, and this is the, and as you see, we have not performed any big smoothing, so these are really built up, and we will now, you know, there's this the major transport take place here through the Makassar Strait. We also look for transport through the Ombai Strait. So this would be the western gate of the ITF, and then we also look here for the eastern gate, the Ombai Strait, and the Timor Passage, where we also get part of the Indonesian throughflow out. And therefore, these are the main regions which we take into account later. But we simulate the entire domain here to make sure that the boundary data that we apply do not disturb the simulation results too severely. So this is always also a strategy in modeling to make sure that your results, that your open boundaries are far away enough that the distance between your open boundaries and the region of interest is long enough, so that the boundary values, which I always somehow produce some inconsistencies, that these boundary information does not disturb the important signal of your region of interest too severely. Okay, before using such kind of model, it is always very important that you do some kind of, that you check if the model is giving correct results. And this is done by model, as any modeler knows, by model validation. And model validation means that you just compare your model results, your theoretical, as you would say it, model results with realistic data, and the most realistic data that you can get hold of are observational data for sure. And therefore, the optimal situation is that you have some observational data available, and then for specific periods, and then you can compare your model results with these observational data. And this is also, fortunately, we have some data available for temperature salinity from satellites, and we also have some transport data available through the from the INSTANT project, which provides very good what's the best data set on transport of the ITF. Okay. Are there any questions up to now? Or what did you think? I should answer some questions? Or there's no question? Sorry, I need some. Let's show just getting. Okay, then I will continue looking at the model validation. The first thing we did is that we compared our data with the first here the numbers in the areas where we have some temperature data available. Sorry, some salinity data available from the ESMOS satellite, and this is from the year 2010 to 2012, where we did this, where we really run the model for this period with the specific forcing for this period in a hindcast mode, and then we compared these data at the different stations here, 1, 2, 3, 4, 5, 6, 7, and compared these data then with our HAMSOM model results. And you can see that the red line is our, I hope so, where did it say? The red line is our model, always our model results, and the black lines, they identify the observational data from satellites. And you can see that for most of the stations, there is quite a good match between our observed and simulated temperatures. In particular, here for some station 7, for example, which is here in the Banda Sea here, there you have you match also this the seasonal cycle is nicely matched here, and also for station 6 here in the Java Sea, you have this very nice match between the observed and simulated data for the salinity. So, and we must admit that the observations show a little more stronger tendency to stronger variations, which we cannot really always catch in our simulations. But I think the general order of magnitude is very nicely fit, and we also, at least some of the variations that we see are simulated quite nicely. So this is just for 3 years, as you see. And then we have also temperature data available from the MODUS data, MODUS satellite. And this is from longer time. This is from between 2000 and 2012 at 3 stations, A, B, A here in the Malacca Strait, and here in the eastern area, and B is here on the off this coast of Sumatra. So there we can see that this seasonal cycle of temperatures, the observed one, the black one, is quite strong, but the simulation just show nearly the same. And even if you have some kind of outlier here, for example, in 2000, this is 2010, you also find that your observations are that way where the observed temperatures are in the winter are a little bit lower. You will also see that this is the same match here as you have for in the simulation as well. And also this is the same is true for stations B and C. For example, here station C, I think, is really the best, shows the best fit for the year 2005 here. We have also this extreme negative values in the observations, and this is also simulated. So this is, I think, is a very nice proof that with respect to temperatures, our data, our model results are quite good, and this gives us the some confidence that our model is able to simulate temperature and salinity distributions quite realistically. And looking at the transports now, this is the first guess here. We have just calculated the seasonal transports or the integral transports through the different straits here. Malacca Strait has on the one hand is the first figure shows you the observations. Don't ignore the value in brackets, and then you have the upper line identifies the transport in the simulated transport, while the lower line is observed transports, always in Sverdrup. And you can see that in the Malacca Strait, for example, we have 0.1 Sverdrup. Minus just means that it's running in north-south direction. So this is the minus sign indicates this. For example, in the Makassar Strait, we have also transport of observed transport of 12.8 and simulated transport of 12.8 in south direction, as you would assume. And there is the transport, the observed ones are between 10 or 11 and 12 Sverdrup. So this is also quite nice. But in this Flores Strait transports, we have 9.1, or what we can check here also the Ombai Strait transport. They are a little bit lower than the observed ones, but also there is some. It's not a big. It's not really clear for which period these observations have been taken. But in principle, we can say that with respect to the transports, we are in the correct range in our simulation. Okay, then we have made more closer verification of the transports. Just ignore that the model data is mainly here the thick red line, and then you have the purple line are the observations. So this is, and you can see that for the Lombok Strait, the comparison is quite good. We have distributed here between different layers. So therefore you see here in the upper left figure, you see the transports through the in the depths between 50 to 100 meters. Then in the left lower figure between 100 and 350 meters, and then we have the on the right hand side there is the between 100 meters and 150, and then we have 100 meter to 750. So this is for the very deep. There you can get information on the very deep information, on the deep transport. But if we just check here, for example, in the upper layer, the match is quite good, and also here in 100 to 150 meters, there's a stronger internal variability in the observed transports from the instant project, but the general structure looks quite confident. So this is for the Lombok Strait. The results are not, at least they're in the right range, and also the range of variability is acceptable with respect to, if you compare your model data or model data with the observations. We made also the comparison for the Ombai Strait, and this is the same here for the upper layer. There's quite a good match. The model results are the blue line, and the instant data are the purple line. You can see that, for example, here in this is for 2004, that between May and June here, we have, for example, an observed peak in the transports in the Ombai Strait, and this peak then is matched also from the observations. No, sorry, excuse me. No, 2 hours, sorry. But there was the room service, sorry. Okay, so I think also if you look at the deeper layers, 100 to 350 meters, the observations here, again, the purple line and the model data, they really have a very confident match. So we are quite happy to see that at least we think that our model results are quite good for this area. The same we checked for the Timor Strait, where admittedly there's the general structure in the upper layer also looks not bad, but we have also some mismatches here in the deeper layer. But I think this is always what happens if you have such kind of model. Okay, I think this is now, so we can be at least quite confident that our model produces reasonable results. And now the question is, can we show some of or what are the in the reason? So this is already, these also are already some results, but because if you show the validation, then you also have to show already results. But this gives you at least this comparison, tells you that the model produces good results. And now you can assume that also for perimeters periods where you don't have any comparison, also the results are not in a realistic range. Okay, sorry, I have to have some water. Do we have some? I would be very happy if someone asked a question in between, so that we have a kind of discussion. Agus, do you have any question, Agus or Agus?
Yeah, anybody, if often we do presentation first, then Q&A, but
okay.
If you prefer more, like back to back,
yeah,
forward, that's fine. Actually, I have a question since
yeah, very good. Appreciate that.
So it seems like around April and May, in Lombok and Ombai, and also different. It seems there is a bit consistency in having more, I guess, bias during those months. It's just interesting to see that it happens in different sites, also different depths. What do you think the underlying reason for that? I mean, why it's always around April and May?
Okay, this is a very good question. I could imagine that there is I think our major problem is that so we have our forcing data, they are quite, this is the hindcast data, they are quite consistent. I don't think that they produce any problems in this respect. I would more assume that there is our main, the main purpose for uncertainties is the mismatch between our open boundary values from our large scale model and our in the regional model. I would guess that for these, this is just a guess, that for these periods, the mismatch between the information from the large scale model and the regional model is large. So this is, I think this is our main problem, that we see that the large scale model at the end is has a little too coarse resolution to really give very totally exact boundary forcing data. And we have to do some lot of interpolation and so on. And I would guess that in this period, the mismatch between these different model scales is producing the largest errors. Yeah, would be my answer to your very good question. But at the end, you're right. Yeah, this is a good point. Yeah.
It could be something to explore, because it seems to be around May and April. Although
you're totally right. This is fully clear. I also saw this. Yeah.
Maybe someone else have a question, since we can do this as well, Q&A in the middle.
Yeah, it's, because I think it's better to have it just after each part of information, because then we have it really in our minds. So.
Okay. Someone's raising.
There's a hand. Very good. Yeah.
Go ahead, Ibu Adiana Pratiwi.
I'm very happy to see the presentation. I would like to, in fact, I would like to perhaps if you have more time at the end, I would like to know more about the model you use, especially the mathematical model, and how you solved it.
Okay, yeah, this is a good point. I have some slides on this. Okay, then I will bring this at the end. I mean, there's another.
Thank you very much.
Okay, I can do this very easily. Yeah, this is good point.
Great.
But if I should forget it in the hurry, just give me a short reminder that I promised to do it.
Okay.
Thanks. It would be very nice.
Okay, very good. Yeah.
Yeah, this is great. I think I mean, you could continue, and anybody who wants to have questions in the middle, feel free to just raise hands and we can start.
Yeah, perfect.
How about that? Yeah, okay, good.
Yeah. Because I always like to have some kind of interactive presentation. For me, it's better if you do it via Zoom. It's such kind of unpersonal, and if you at least have some kind of communication, then it's I always appreciate that. Okay.
In fact, if anybody would like to, open their camera, it could help with the interactions as well to see.
Yeah, this as well. Then you can see the face.
Yes.
I appreciate to see your face. And
okay, thank you.
This is already very good. Okay. Okay, then I will just continue. Yeah, we have some results here on the ITF transport. And then we also, this is the Makassar Strait. Then we focus a little bit on the Makassar Strait transport in detail. Okay, this is the general sketch that I showed you already. This is the very average transports for 3 years' time for the upper 420 meters that we simulate, and you see that most that are strong you see the arrows, and you see also the color shading, which indicate that most of the transport is really going through the Makassar Strait here. But there's also some other branches which also feed to the Indonesian Strait. Okay, but we go a little bit into detail here. What happens for the over the total depth, the transport that we see here for the ITF is shows a very strong seasonal variability between in winter time. I just say January, winter time here in January, and can also say in January, February, and so on. We have transports around only two sphere drop, and they increase up to 28 sphere drop in the mean. But we also have a variability here about so they can go up to standard deviation is really double of that. Okay, and then we see, if we really look at the distribution over depth, then we see that in the upper 50 meters the transports are quite small, and they even show in some seasons here in the beginning of the year, they even show into the opposite direction, so pointing to northward, and only in the but they are around not larger than 2 sphere drop. And the strongest contribution of the transports comes from the section between 50 and 300 meters, where you get up to 10, 12 sphere drops here. But this also shows this the same seasonal distribution, that in the beginning and the end of the year, transports are much smaller than in the high in the middle of the year. And this is just mirrored as well in the deeper layers here. So they are quite similar, and even shows for between 300 and 700 meters, you see such kind of same transports in the same range as well. And also below 700 meters, we still have quite significant transport. So this shows that it's a really deep region. You really, that there is really a deep reaching circulation going on there. So it's just quite clear. It's not just wind driven or Ekman driven. It's really driven by some other processes. Okay, so the general, the average transports are given here now. So as it said, the total transports is around 11.5 sphere drop, and it distributes over the surface layer, just makes a very small share of just 0.5 sphere drop, while the layer between 50 and 300 meters has 6 sphere drops, the largest contribution, but also and the rest of the contribution, which is around the same amount as in the reaches 3.8 sphere drop and 2.7. So it's also made up to 6 sphere drop. Okay, but this is, as I should mention, this is the climatological transport that we simulated. We have this simulation between 1970 and 2006, and we made this the average over this entire period, but for the different months, so that to get this climatological values.
We have a raised hand.
Yeah. Oh, there's a hand. Very good. Yeah.
At Do Yoga.
Okay. Thank you, Bintan. Can you hear me?
Yes, we can.
Yeah. Yeah, we can hear you.
Yeah. Thank you, Professor. Just I have some question. First is do you include the explicit tides in your simulation? And the second is what is your river forcing? Is it a monthly climatology or yeah? And then the third is, do you have any comparison the transport between your specific model in Indonesian region and the transport coming from the OM MPI?
Your first question, I did not understand the word. Can you repeat your first question?
Do you include tides in the simulations?
Tides. Okay. In this simulation, tides are excluded, so they are not included. Although we have in our model, we have a scheme to these tides are easily it's easy to use them, but we in this simulation actually we excluded the tides, because then it's more difficult to get some mean values, because then you always have to look for integrate over longer periods. So tides are excluded in this specific simulation. We normally in our HAMSOM simulations we have the tides are included, but not in this case. Your second question, this is the forcing is, as I said, the NSAP data, and NSAP is really realistic 6-hourly data. And NSAP.
Sorry, Professor, for the river forcing.
River forcing.
Yeah.
Okay, this is the river forcing. For the river forcing, we made some. This is very nice, good question. We have our own hydrological model, which is with comparison with yeah. Okay, this is we have the rivers. There's a hydrological model that we got from colleagues in Frankfurt, and they just calculate on the basis of the precipitation for the different catchment areas. They calculate the specific river runoffs, and we have to do some. This is giving already quite good results, but we did for the larger rivers. Then we did some kind of correction of these data for specific periods where we have river data available from Indonesian sources. But this is was a good point. But in principle, I would answer we use a hydrological model based on precipitation data to simulate also the river runoff for our area. Yeah. And your third question, what was that?
The comparison of the transport between the OM MPI global and with your model in Indonesia.
Okay. Yeah, this is brings me nearly back to the question, to the previous questions. The MPI just has a very rough very rough resolution of this ITF region. There's just one grid cell also. Therefore, it doesn't make sense to compare. So this one grid cell is not, so the principal data transports are okay, but you cannot really make this comparison in a reasonable manner, because the large scale MPI model is too coarse for this area. So this is and therefore we also had the feeling that sometimes the blocking of this is too strong, or even not strong enough for different periods. And this brings me back to the problem that we faced between the mismatch that we saw in April and March. So actually the MPI the bathymetry resolution is not really sufficient to make a reasonable comparison here. Yeah.
Okay, thank you, Professor.
Okay, very nice to have some questions. Very good. Okay, there's another hand. Yeah.
Can
Hello.
I ask directly?
Yeah.
Oh, okay. Professor Pohlmann, I'm a microbiologist, so I just have a curious question. It's probably a naive one, and I'm not sure if I'm following it correctly. So I see here for the transport for the first 50 meters, it's positive, and the rest, I mean, starting from 50 meters below, it's getting to be a negative. Could you explain more? Is it because of for the first 50 meters, there is an influence from the river forcing, as you explained in the previous question?
No, I think this is it's a good question, but for an oceanographer, it's actually quite easy to answer, because the upper 50 meters, they are strongly affected by the wind. And what you see here is just the effect of the change of the monsoonal winds. So this is, and since the lower layers below 50 meters, there is very low impact of the winds anymore. So you won't see this this effect of the reversal of the wind patterns. But this is for the upper layers, you directly see that. So this is just the monsoonal influence that you see. But it's definitely something which is, as an oceanographer, you know that the wind is not an effect, not a strong effect up to below 50 meters. So I would say in this area, probably you will also have an influence up to 100 meters, but it's getting strong. Yeah, the exponentially weaker now.
Okay.
Yeah. Okay.
Okay.
But
thank you for the explanation.
Yeah, okay. Okay. Should I continue? Okay. Then now we have a stronger focus now on our main simulation, our main through flow area, the Makassar Strait, and so we see what is going on there in more detail. So now we focus on the red box in our simulation, and so we made some also for the years 2004 to 2006. We looked at the vertical distribution for the different seasons: January, February, March, April, May, and also for summer, and here for autumn. And we can see that there you will always find some, and in the overall, the black line here, it shows that there is some kind of reversal. There's a internal maximum, what you call it here, so the maximum of the negative flow, which is always in a depth of about 100 meters. And then you're going further up, the transport are getting smaller, and also if you get then into the deeper areas, you get also this weakening of the transport. And the interesting thing is that there is some kind of seasonal variation in this pattern. So for the high summer from the middle of the year, this is this maximum moves to shallower areas to, let's say, around 80 meters or so on, while in in spring and autumn here, you will have some kind of 100 meters. You will meet the average value, and if you're going then to January to the beginning of the year, you will also go to slightly deeper layers. About the maximum is a little bit deeper, around 105 or 110 meters. This is something which is quite special, and also the magnitude is changing a little bit. So you can see that you get the highest transports you will get in April, May, June, while lowest transports are there. The transports are around the velocities are around 0.6 meters, or even stronger, 6.5 meters per second, while in the let's go back. While in autumn, the transports are much weaker. They just reach a maximum here around 0.35 meters, 35 centimeters per second. So this is also a strong an indication that there's a quite strong seasonal variability on this transport. Okay, now we go to the next slide here, which gives you the should tell you how the this is the main transports here that you see, but now you see the main velocities, and now you see here how these velocities are changing over depths for the different. So this is just the we have here some diagrams which shows for the depth from north to south. This is a northernmost, then this is the second northern, third, and the fourth. So this is these different dots here where we made some isoplates. So this is the distribution in January 2004 to June 2007, as it says. And you look at the velocity, the strength of the velocity blue indicate that there is a negative transport, and you find that there's quite a strong seasonal variation here, and also variation as well in the vertical. So you can also see this inversion of the current in the surface that we see at the beginning of the year for the different years in the northernmost parts. And the strongest values we find here is directly at the surface, sometimes at the end of our period. I would say that if you go further south, then you could see that the maximum is somehow not focusing on directly at the surface anymore, but it's moving a little bit to the deeper areas. So this was the first 4 plots, and you can also see that some kind of if you're getting closer to the bottom or to the deeper layers, that you always sometimes see quite a reversal of the flow. So this is also happening because then you get these reddish colors, which indicate that there is some reversal of the flow, which temporarily happens then, but only in the deeper layers. So coming then to the last 4 circles here that you see, then you see that this movement to the deeper layers of the maximum transport is even increasing there, and there the periods of reversal are not so strong anymore. So I think it's also some indication that there are that there's quite a strong variability going on there. And now we have one interesting information is that if you look at the transports on a very short time scale, so just look for a very short period. Now I think that there's a movie starting just from 25th January. This is just different days here. This is just day-by-day variations. It's very short-term variation. And you see that on the day-by-day, this is here always the date, you see that there's at the beginning again, that there's quite a strong daily variability on these transports. And this daily variability, yeah, I think it's quite obvious. This is some kind of there must be some kind of wave going through this. And there's the hypothesis by Alan Gordon and colleagues that this area faces that there are some Kelvin waves. This is, for example, the same here. You see to show this very short-term variability in the system. Here, for example, at 30th of January, there is no maximum here, while 4 days later or 5 days later, you find a maximum of the transports here. And if you then continue for another 5 days, this maximum is increasing here. And then oh, sorry, let's go too far. And then it's really strongly changing. And the explanation by Alan Gordon and his colleagues is that there are some Kelvin waves running through the system, which cause such kind of this short-term variability. I think we should focus on, we intended to focus on these Kelvin wave hypothesis stronger, but then the project unfortunately is finished and we could not follow this. But this would be at least some idea that the people could do to find out why we have such a strong short-term variability in the system. Okay. I think we have now the hypothesis of this, what is causing this Indonesian through flow really? What is the physical cause for this? It's also by Alan Gordon and his group. There was always the hypothesis that the pressure head is causing this, which means that the difference between the pure barotropic pressure in the Indian Ocean area and in the Pacific Ocean area is causing this. So this means that in principle, the sea level in the Pacific is higher than the sea level in the Indian Ocean. And we try to support or find a proof for this hypothesis. But if we look at our dynamic heights that we calculate from our model, so this is the general, the heights, the sea level, which really affects the transport, then we can see that the heights, calculating these heights in the Indian Ocean and in the Pacific is not, the Indian Ocean sea level pressure is even higher than in the Pacific area. So this does not, at the end, our results do not confirm this pressure head hypothesis, because looking at the dynamic heights, there is not a proof for that. It's even vice versa. So there must be, we have not really, we also discussed this with Alan Gordon and his group, and there is no real clue on why this through flow. So the real cause for this through flow is still not clear. There's another hypothesis that we at least try to promote, is that this is caused first also by some kind of inertia, that the strong equatorial currents in the Pacific Ocean, they put some strong inertia on the currents in the in the through flow area, and that this inertia is really the governing cause for this through flow. But there's still a lot of we still have no final clue on this. Okay, this brings me to the conclusion. HAMSOM of this part of my presentation. HAMSOM and the MPI is a powerful team. We have already, in the questions in between, we already saw that the MPI-OM, at least at that in this simulation which we use, was not fully. The team has some weaknesses because the MPI-OM resolution was not in the in these in this setup which we use was not really, it was a little bit too coarse to give really very correct boundary lines. We make some questioning on the driving forces of the ITF, so the pressure head is from our results cannot really be supported. And Makassar's through flow we investigated. And in the northern part, we saw that the flow is more focused at the surface, while in the southern part, it's more subsurface. And for the winds, we showed in another study that they have some kind of decelerating role. So they can also not be made, so the local winds can also not be made responsible for this through flow. There must be some other reasons for that. Okay, this brings me to the end of this part. Is someone having some questions? I will need some water at the moment.
Okay, if anybody have questions, I guess I need to remind there was a question about the math.
About the
math.
math. Okay.
Yes.
Yeah, okay. How much? Okay, yeah, very good. How much time do I have at the end?
You still have time. We often, yeah.
I expected to have 1.5 hours, so until 9:30?
Yes.
Okay, so this is quite good. Then I just can finish the next, I can start with the next part, which takes about 15 minutes, and then I go back, try to find my slides on the math. Yeah. Okay, very good. Yeah.
That's good.
Perfect. Okay. So this is the up to now there was no real information. This was the this is just hindcast simulation. So there's in these hindcast simulations you could also already see some climate change, because also in the hindcast period we have some climate change, but we also did some simulations on real climate change forecasting or scenarios and the keyword there is a regionalization of global climate change simulations, which we do. And so you know all about these climate change, the IPCC report, which provides information on for different scenarios here. So this was 4.5 scenario, which is the we would say most reasonable scenario for the future, because you always have to make some assumptions on the human activities and the release of CO2 to the atmosphere. And due to these, and this 4.5 scenario was at least supposed to be one of the most realistic scenarios with respect to the behavior of mankind. And there is now, looking at the temperatures for the different seasons, you see that there is an increase in all areas, and in particular the Arctic Ocean shows the very strongest increase here, and but also the Indonesian areas show some kind of increase of around 2.5 to 3 degrees here. This is something which is, and this is just a moderate scenario. In the higher scenarios, you get even increases of 3 to 4 degrees. But the drawback of these global IPCC scenarios is that the results are, as you can see, for example, here on the right-hand side, there is just the best you can get, that for the Northern Asian area, that there is the resolution is quite bad. So you cannot really, if you are, for example, interested here in the Bohai Sea in China, there's just 1 or 2 grid points, almost 4 grid points in the simulations, and this does not really help you to look at the differences or at some local processes or local phenomena here. For example, if you're interested in sea level rise or some storm surges, and this very bad resolution of the IPCC scenarios does not really help you to get information for the regional scale. And this would mean that you have to do some downscaling of these global results. And this is our main focus for a long time already, that we use our regional models, also the HAMSOM model, to downscale the information from to make some downscaling from the global scale to the regional scale of areas that we are interested in. And we have in a recent project, what we did is that we made this downscaling for the East Chinese Shelf Seas. There was a project with China And we did this, and the approach is quite obvious, showing here in the sketch. We have the error data, which are the for the hindcast. So we always have a hindcast period where we have the error data, which I already mentioned, which feed a regional meteorological model, and then there is the MPI-OM model. In this case, we just use the MPI-OM because the resolution was sufficient now. So because we modified the MPI-OM model in this respect, that the resolution in the Asian areas is much better now. This is this is another gimmick here, that the MPI-OM which we used has a zooming grid, and you could, by shifting the poles, you could modify the resolution in different areas. This is very specific for the MPI-OM model. By the way, the MPI-OM model and the HAMSOM model, they are of the same origin. So the originators, they have been by two persons originate developing this model, and then they split after 10 years or so. These models are then split into two models, but in principle, MPI-OM and the HAMSOM model are the same, or are very similar with respect to the numerics and to the setup. And if we have confidence doing these hindcast simulations in this way, then we did some information, and then we did the scenario runs, which means that we use some from the Earth system, from the ECHAM, from the atmospheric model, which is run for the IPCC scenarios. We force our regional atmospheric model, and then we use our MPI-OM model to be forced with this. And the important thing is that we have the feedback here from the MPI-OM model to the REMO data, to the REMO model, to the regional meteorological model, which means that there is an interactive coupling between the atmosphere and the ocean model, which is an important factor to get realistic results. So this is quite important, that there's a feedback between the ocean and the atmosphere again. The MPI-OM model in this area has a resolution of around 20 kilometers, which is sufficient at least to get the transports we are interested in. This is just one of the results here. It shows that the temperatures in this our East Chinese Shelf area, how temperatures are changing over time for between 2000 between our hindcast period and our forecast period in the years up to 2100. And you see that there is some, in winter we have an increase of around 2 degrees here, in particular close to the coast, while in the ocean areas there's just an increase of around 1 degree. So this is somehow, this global warming is damped in the ocean areas, but there's an increase in the shelf areas. And the same is for the summer situation. It looks even worse. There's some kind of increase here in of around 3 degrees, in particular in the area where you have the outflow from the Yangtze. This is the largest river here in China, and it has a lot of, and the freshwater runoff is increasing, and while increasing the freshwater, stratification increases, and this increase of stratification also leads to the thinning of the shallowing of the thermocline. If the thermocline is shallower, then there is a specific stronger input or feed into this area and into the same water column, which leads to the very strong increase of temperature, in particular in the area of Yangtze River outflow. We were interested also in the transports, the transport rates, that are they changing? So this is at the end of our simulation period, the transports, you know that there is an inflow in the Luzon Strait, and then you have the transport here through the Taiwan Strait into this shelf area. And if we compare, if there are some changes, you see that there is not a big change in the transport as well. So the Luzon Strait is transport into the South China Sea is reduced in some way, while the transports to the Taiwan Strait are increasing. The transports here at the shelf at the east of Taiwan, they are increasing a little bit, but there is not a changes stronger than 10% or so, which is quite was not expected at the beginning, but this result show that there's not a very big influence on the transports through the boundaries of the East Asia on the Eastern Chinese Shelf. Okay, looking at the temperature distribution, then we compared the scenarios and looked at the integrated temperatures in this in our on the East Chinese Shelf, and we compared the two scenarios here, the 4.5 and the 8.5 scenario, and we can see that the temperatures, the surface temperatures here, the upper plot, the upper lines show the surface temperatures. The red is the 8.5 scenario, increasing up to the year 2040. There is not a big difference, but then the 8.5 values are shooting up to much higher values, while the 4.5 values are nearly constant. And this is the same is somehow true for the bottom temperature. Looking at the salinity, the signal is not such clear. It shows that the for the different scenarios, the salinities are not somehow quite in line. There is some kind of 8.5 shows some strong lower salinities, but there is also some kind of up to the year 2060, but then the values are getting somehow not consistent anymore, which means that the system also has a strong amount of internal variability, which is then it's not totally forced by the outside of the from the meteorological information, from the meteorological forcing, but there is some kind of also internal variability, which then makes that there is not a consistent set off anymore from the 8.5 compared to the 4.5. Okay, I think this is everything on this. I have a little bit time. I will just tell you our carbon cycle model, which we use then as a add-on onto our model system, which we developed for the through flow. We were then in another project, we were interested to look if there's some changes in the carbon cycle. And this is perhaps a little more interesting for biogeochemists and biologists in your group. The first thing we have to do is that we had in this carbon cycle model, we need to have the partial pressure of CO2, and we developed a time series of this pressure, and you see that there's some kind of nearly linearly increase of the CO2 from 1958 to 2018, and this is this line which we used as a forcing, the main forcing for our carbon cycle model that we have to do is that at the sea surface you have to impose some partial CO2 pressure. Okay. The results look quite as you would expect. This is now the partial CO2 in the water that you see here, and you see that there is this mirrors this linear increase. This is average over our Indonesian shelf area, and you see that there is an increase of the partial CO2 pressure, just mirroring the forcing in the atmosphere. And looking then at the pH values, you see that there's the same quite the decrease of the pH is just totally in line with the increase of partial CO2. So there's some kind of inversion behavior between PCO2 and pH, which you would also expect from chemistry. looking, then we have some other values. The alkalinity is somehow increasing as in the same range as you would expect. And then we have also the dissolved inorganic carbon, which is increasing due to this more dilution of carbon in the water. This is something which is also somehow just totally mirroring the imposed partial CO2 pressure in the atmosphere. But you see that this is not just mirroring. You also have some variability, which is not, it's not just a very easy. There is also some kind of variability in this line, which is not directly connected to the input from atmospheric CO2. Okay, then we calculated the fluxes for the shelf and the deep sea areas. So we just distinguish between Indonesian shelf areas and Indonesian deep regions. And what we see here, this is the blue line, is for the deep ocean, and the red is for the shelf ocean. And you can see that, and this is just the average for these areas. And you see that the fluxes between ocean and atmosphere is normally there is some outgassing of CO2 in the Indonesian waters. So because and this outgassing is stronger in the ocean in the deep sea areas compared to the shelf areas. But the interesting thing is that beginning of 2006, for some seasons, we see that there is some input. The flux, the CO2 flux is reversed, which means that due to which is caused by the fact that due to the increased atmospheric CO2 pressure, now there's a tendency that for some seasons the ocean is now becoming a sink for CO2, and so this is something which is changing due to this strong increase of CO2 pressure in the atmosphere. And this is something which we could find out with our simulation, that there is this kind of shift in the system from beginning of 2006. The oceans temporarily becomes a sink for CO2, which is different than for all the periods before. Okay, if we look at this in the horizontal distribution, you can see that the blue is always the outgassing area, and so the shelf is for February, for example, you always have such kind of outgassing, while the ocean areas is sometimes because it's colder, it can also be a sink of CO2, but on the average, you see that most of the area is an outgassing. Okay, yeah, I think I will just shortly refer to this. We also looked at in our carbon cycle model, we included the processors, some kind of, to very rough estimates. We included coral reefs here, corals as well, in the spots where you see here, there's some kind of cover of corals, which we got from some atlases. We looked at the coral distribution, and then we included this coral distribution in our model, and then we looked at what is the behavior of these corals to the carbon cycle. And the major thing that this is now the last slide on this, the major thing that we see we have for different seasons. This is on the left-hand side without coral activity, and on the right-hand side we have it with coral activity. And this is again the CO2 fluxes that we see. Again, the blue is the outgassing, and red is sink behavior. And what you see is that on the left, this is for January 2014 and July 2014, and on the right-hand side there is the coral activity is included. And what you can see is that you have in specific areas where there is a high coral concentration. For example, here in the south of Malaysian island. It's a Malaysian peninsula. You see that there is an increased outgassing then. And this is due to the fact that the corals are degraded in these areas, and therefore there's a production of additional carbon in these areas, which leads to an additional outgas. So this is our the clue on this our carbon cycle model with a combination of these of the corals. I think this is everything I want to tell in this respect, and perhaps we have some questions on these matters, and if at the end I can give you try to find my slides on the mess. Yeah, thank you very much for listening to this part. Thank you.
Yay, thank you so much. Well, that was very comprehensive presentations from A to Z, from the models, from the performance for the transport of the ITF. That was really interesting. I was actually really hoping that you would show that biogeochemical aspect as well, and as well as the coral studies. So here with us, not just from the RC Research Center for Deep Sea, but we have also colleagues from Research Center for Oceanography from universities, so with different backgrounds. So if anyone have questions, it could be related to your aspect as well. We have biologists as well in this forum, so please feel free to ask. I think we can ask many questions with all the different aspects that we have heard. Silakan Bapak Ibu, kalau ada yang ingin ditanyakan, bisa raise hand, bisa langsung juga silakan.
Yeah, Ibu Intan. Yeah.
Oh, silakan Pak Agus.
Yes, my question is related to your IPCC scenario and also the variability in the ITF region. How about the trend of the global climate change to the variation of the transport in the ITF region, and what is the impact globally to the climate?
Yeah. Okay, this is a very good question, and as you have seen, we have not in this project where we worked in, we have at the end we intended to also run some climate scenarios, but the ITF results I show you are just based on hindcast simulations. So therefore, unfortunately, I cannot give you good points here. This should be studied. We have the tools available, and but to answer your question, we should have a new project then, and try to simulate also do some scenario forecasting. So at the end, I cannot really give a good solid answer to your question. Sorry, but this is just due to the fact that this was just we just established this model system for the hindcast period, and the scenario forecast was intended, but we could not finish this at the end. Sorry. But the question for sure is reasonable, and I'm also very curious about this. But it costs a lot of computing time and effort to answer this. But we have the tools. We would have the tools available. Thank you very much.
Yes, that is actually a great motivation, because I was actually involved in the IPCC for the chapter 9 on the ocean part, and we did discuss about presenting more of ITF, but we were actually having difficulties trying to gather more studies. So, you know, on the IPCC's end is about, okay, what new studies that we could assess, and there's also difficulty that the time difference between the IPCC 6 assessment report and the special report on the oceans and cryosphere was very short. So, but yeah, this is a great motivation. If we can have more studies on the ITF, not just on the observations, the modeling, and all these other aspects related to the biogeochemical, that could be a really great materials for the next IPCC report.
Yeah, I totally support your point.
Yeah, we were having difficulty with that.
As I said, we have the tools available. It just needs a little bit of a project which is then allowing us to perform these studies. Okay, but I think also this would be a very important additional information, and I also don't see any studies on this in the literature. So this is really some kind of black spot at the moment. Yeah.
But it's also worth mentioning that in the last assessment report, the 6th assessment report, we have defined the ocean region better, because in previous report it was more like very blocky terrestrial oriented kind of regions for IPCC report. Yeah. But starting last time, we for example for Southeast Asia, we have a more clear sort of Southeast Asia region. So that'll be also interesting contributions, how we can focus more on Southeast Asia and have studies on this, how the oceans and the ITF changes in the region. Yeah.
I think it's a good point, because if you have the definition of the areas, this already gives you some kind of starting. If there is no real definition of areas, then people are not really interested in these areas. But if you have the definition, then there is a question what happens in these areas. So I think this is a very important step to get these definition of the areas correctly and in a way which is also supporting oceanographers. I think this was a good way to initiate such or to promote our research. Very good. Yeah.
Thank you. Okay. Do we have more questions? We have 7 minutes before 9:30. I don't know if Dr. Pohlmann has already have your breakfast.
I have my breakfast.
Oh, you're good.
Yeah. I was getting up quite early.
Okay. Okay, we have a question for Putri. Silakan, Mbak Putri.
Thank you. Okay. My name is Putri. I think it's a really interesting topic for today, but I never done with the HAMSOM model, and my question is, maybe this question is a really basic question for you, because I often heard about the other model like AGCM or OGCM, but I never heard about the HAMSOM model. But my question is, why do you choose this model for answer the driving mechanism of the ITF? Because I heard about, I listened your presentation, but I'm still, what is the special of the this HAMSOM model? Could you explain me? Because I just read your article about the regional model HAMSOM has been successfully applied to the region of the ITF. For long-term results show that there is an enormous variability in the current system governing the transport. More than 80% of the ITF is transport within the upper 700 meters of the ocean. How about the below like 500s? How about the result of HAMSOM models? That's my question. Sure.
Okay.
Thank you.
I think if there is no other question, I would then really, because this is the second time I was asked about the specifics of HAMSOM. So should I just present? I have 2 or 4 slides on the, or 3 or 4 slides for the HAMSOM model. Then I just would try to, I know where to find them. Just 1 second.
Okay. Okay. And you do you also use this HAMSOM model to the coral reef? Yeah, this coral reef. The last slide. You mean?
Mm-hmm.
Yeah, the last slide.
This is easy. I can answer this in between. This is the HAMSOM model is just a circulation model, which provides the circulation patterns, and therefore it is not. This is important. The circulation is important also for the distribution and the dispersion of the chemical substances. But to really use the carbon cycle model, you have to have this is a different model which makes use of the results of the HAMSOM model. So there is some input from the HAMSOM model into this carbon cycle model. So at the end, it's a separate model, this carbon cycle model, but it needs the information from HAMSOM model to get the correct advection term, the correct transports of the different substances in the area correct. I think this is how you could answer this. So this is not just but this is very, very common that you have to run the circulation and transport model. If you have this available, then you can have some add-on models, for example, to simulate the fate of pollutants, and here, for example, the carbon cycle, or even for larval transport or some other biological models. So I just found it where I want to go. I'll just in a second.
Okay, thank you, sir.
Yeah, I hope. Yeah, but now I will
Nice answer.
Answer the next part of your. Oh, now it works. Yeah, 1 second. I'll just go back to this one here. You can see me in the. You can see this slide now.
Yes, I can see your slide.
Okay. Okay, this is good. Then I just make it here. I have some. I'll just do my best to. Oh, okay. So now I got it again. So you have this is the details of the HAMSOM model. Okay, I will just. Oh, this is the.
Okay, while we're waiting, you probably want to open your camera so we can see who's behind the microphone.
Okay, yeah. So this is the details about the HAMSOM model. This is the shallow water equation model, and it has the vertical momentum equation. This is quite a standard shallow water model. So you can see them, these slides? Okay.
Yes, sir,
okay,
I can see.
And then we have the temperature salinity transports are also included. So there is no real miracle about these. This is used for nearly any model in the world, and the specific thing for the HAMSOM model is that it is, as you mentioned, all these AGCMs and OGCMs that you were mentioning and referring to are global models. So they are simulating the entire globe and the entire the processes on the entire Earth, and this makes it. Therefore, they are not able to run in a very high resolution, because if you're the computers nowadays still are not permitting to run really on a global scale simulations on with a very fine resolution, and therefore this is the reason that you also need information on the. Now I have it. That this is therefore you also need to have regional scale models, which just simulate a specific area of the world ocean. And these areas, these models are then called regional models. And this is the HAMSOM model, is a regional model which has some kind of specific aspects, which I just okay. This is just the, it just shows some specific aspects on the regional scale. I will just, on the next slide, I hopefully see, yeah, this is now the specific things for the HAMSOM model. It is defined on our cover C grid, which is quite important that you have this grid, because if you're simulating tides, then the C grid is there's different staggered of the different components. Temperature, salinity, and velocities and sea surface pressure are defined on different grids, parts of the grid, and this our cover C is a prominent, is the most favorable if you want to also include tides, and therefore we have this. And we have it's a 3D model, which means, but nowadays all the models are 3-dimensional. And but now the very specific thing of our HAMSOM model is that it has an implicit formulation for terms that limiting the time step. And this makes it very special that this implicit formulation is not many other models do not have it, and therefore they need a very short time step. Since the HAMSOM model has this implicit formulation for terms like the vertical shear, diffusion terms, and the description of the gravitational waves, which are the fastest waves in the system. So these gravitational waves are formulated implicitly. This makes it favorable to run it also with longer time steps. And only with models who have longer time steps are able to do some climate simulations, because if you want to have a long-term run, it's not possible to simulate do simulations with a very short time step, but you have to have a long time. The model must be able to run also with longer time steps, unless you will not be able to simulate really on the climate scale about 100 years or so on. So this is just for case studies. You can afford to have very short time scales. And the other thing which HAMSOM makes it very special is that it's very nicely adapted to the to supercomputers, because we have, as I already mentioned at the beginning, in Hamburg we have the Climate Research Center, the computing center for climate research, and we have access to the fastest climate computers in Germany. And but to use these computers efficiently, there must be an adaptation of the model code to these supercomputers, and this is not very easy, but it's very important. Otherwise, you would not be able to run these models in a climate mode. And we did it, this parallelization, so you use many processors at the same time, or of the order of 256 processors that we use. And we do this by domain splitting. So we split our domain into different subsections, and these subsections then are run on every subsection is run on a own processor, which makes the model very, very fast. I think this is the other very strong specification of our HAMSOM model. I think this is the major thing I want to bring to your mind. I think, yeah. Is there some other questions regarding this model system?
I think we might be running out of time, actually.
Yeah.
Yes, sorry for that. Yeah. Yes, let's give applause to Professor Thomas Pohlmann. Thank you so much. This is a very comprehensive lecture. I feel like we should have made a series for you. There's so much to learn. But thank you again. Thank you for your time, and thank you for sharing all this knowledge. Yeah. I think with the diversity of the works that you do, this is very interesting for many of the Indonesian colleagues to collaborate, working on the specific project that have mutual interest. So thank you again. So we're planning, we were recording this, and we usually would upload it on the YouTube. I know some of you were coming late in the morning, but no worries. But I just want everyone to have a focus on what was being delivered as it goes. Thank you again. Have a good morning, everyone. See you in the next seminar.
Yes.
Bye. Thank you.
I thank everybody for his attention and for the nice questions. Thank you very much for inviting me. Thank you.
Thank you. Have a good day.
Yeah, thank you. Bye-bye.
Bye-bye. Let me end the meeting for all. Thank you again, Prof.
Okay, bye-bye.
Bye-bye.